Want to know how a single sentence turns into a 10-second cinematic clip? Let's pop the hood and follow the data. You've seen those demo clips: a neon street, a dog in a spacesuit, a rainy chase. They feel magical, but they aren't magic. Behind every frame is a pipeline of math, compression, and iterative unscrambling. In 12 minutes, I'll walk you from prompt to finished clip, show the pieces that wobble, and give practical tips you can use today. First, what happens the moment you hit generate? That's our high-level pipeline. Coming next. High level, you type a prompt. The app converts words into numbers called embeddings. The generator plants random noise in a compressed space. Then a diffusion network removes noise step by step. A transformer enforces temporal consistency so objects don't pop. Finally, a decoder turns that compressed result into pixels, and optional audio is synced or generated. That sounds neat, but each step hides trade-offs: speed, quality, and energy. Next up, diffusion, the unscrambling engine. Think of diffusion as photographing an image and adding static until the photo is pure noise. During training, the model sees many photos at each noise level and learns small reverse nudges that recover detail. At generation, it starts from noise and applies those nudges, guided by your prompt, until a picture appears. The model never sees your exact prompt during training. It learns the cleanup steps and applies them creatively. Next, I'll explain how training those nudges works in practice. During training, the model watches millions of images with varying noise levels. It learns tiny corrections, pixels to move, edges to sharpen, at each step. Architectures like UNets or transformer-based denoisers predict those corrections. Each learned step stacks into a path from chaos to clarity. At generation time, the model repeats those steps in reverse, nudging noise toward structure. That's powerful for still images, but when motion shows up, a new problem appears: temporal coherence. Here's why video complicates things. Video is just many images in time, but those images must agree. A 24 FPS clip delivers 24 separate images every second. That multiplies compute and multiplies opportunities for glitches. A lamp's reflection shifts between frames. A hand changes shape, or a character blinks out. Models must maintain identity, motion, and lighting across thousands of pixels every frame. Solving that at scale would be excruciatingly slow without compression. Enter latent diffusion, which keeps things practical. Let's open that box. Latent diffusion compresses frames into a learned representation called latent space. Imagine an efficient sketch that keeps structure, but discards irrelevant noise. The model runs denoising in this smaller space instead of on full pixels. That reduces memory and speeds generation dramatically. Once denoising finishes, the system decodes the latent sketch back into full frames, and often upsamples for crispness. You keep essential detail while cutting compute costs, but decoding brings its own artifacts. I'll explain decoding and super resolution next. Decoding maps the compact latent back to pixels with a learned decoder. After that, super resolution and frame interpolation refine edges and add missing detail. Think of decoding like restoring a compressed audio file back to hi-fi. You reconstruct frequencies, then polish. These steps hide most visual roughness, but sometimes invent plausible details that weren't in the latent. That's where realism can slip. So how do models keep stuff consistent through time? Transformers help with that exact job. Transformers excel at sequences. Originally built for language, they treat space-time patches as tokens, small chunks of pixels across frames. Attention lets the model link a patch of a face in frame 5 to the same patch in frame 2. That enforces identity and consistent lighting. In hybrid designs, diffusion handles image formation, while transformers enforce temporal rules. This hybrid reduces flicker and keeps motion believable. Next, I'll show what those spatiotemporal tokens look like in action. Tokens slice the clip into manageable pieces, patches across space and time. The transformer attends between tokens to learn how parts move in relation to each other. That attention remembers that the blue jacket remains on the actor across cuts, and that a lamp's glow follows a camera pan. This tokenization also lets models learn from varied training clips and then generate different aspect ratios on demand. But what truly steers the output is your prompt. So how does text guide the denoising path? A text encoder converts your words into a dense vector called an embedding. That embedding represents style, objects, and intent. During each denoising step, the model checks the current latent against the embedding and nudges the result closer to the prompt. A guidance scale sets how strongly the text pulls the image. Low guidance lets the model improvise. High guidance forces literal matches, sometimes causing odd artifacts. Balance matters, and next I'll explain seeds, randomness, and guidance in practice. Two knobs often change everything: guidance scale and seed. The guidance scale controls how strictly the prompt steers denoising. The seed sets the initial noise. Same prompt, different seed, different result. Too much guidance makes images look overfitted and brittle. Too little leaves you with vague scenes. Pro users keep the seed constant while iterating prompts to refine a look, or change seeds to explore variations. Up next, why outputs still miss the mark sometimes. Even top models produce hits and misses. Ambiguous prompts leave too many choices. Temporal complexity compounds small errors into visible glitches. Training gaps mean the model hadn't seen your exact motion or subject, so it improvises. Hardware and resolution caps create artifacts when you push limits. And randomness, different seeds, gives variety but reduces repeatability. Expect iteration. Next, I'll give practical, director-style tips that make your clips land more often. Tip 1. Write the prompt like a shot list. Name camera, lens, era, and mood. Handheld 35mm, golden hour, slow push in. That precision reduces ambiguity. Tip 2. Use camera verbs, dolly, crane, rack focus, so motion feels intentional. Tip 3. Specify negatives like no text or no extra people to avoid common artifacts. These are small instructions that steer heavy models effectively. Next, I'll focus on how to describe motion and use references to control dynamics. Describe motion, not just objects. Say slow tracking shot follows a character through rain, instead of just man in rain. Use reference images or a short clip for style or motion. Control clip length and aspect ratio up front. Shorter often yields cleaner results. Save seeds for controlled tweaks. Change them to explore alternatives. And when available, use negative prompts to ban glitches. After generation, small edits make a big difference. Let's cover post-processing tricks next. Post-process like a finishing editor. Use super resolution tools to sharpen detail and temporal denoisers to reduce flicker. Maintain the same seed when you want to iterate a single idea. Stabilize shaky frames and color grade for mood. Tools like dedicated upscalers or denoisers rescue many imperfect clips. Small cleanup steps often push a good synthetic clip into something watchable. After visuals, sound transforms perception, so let's look at how audio and video are finally being generated together. This year, some systems started generating audio and visuals together. They build a shared latent timeline so diffusion can shape sound and image at once. That means footsteps line up with strides and dialogue matches lip motions. Models like VO3 co-denoise audio and video to keep sync tight. Benefits include believable ambience, matched sound effects, and cleaner dialogue. There's a lot of nuance here. Next, I'll explain how the shared latent actually keeps lips and footsteps aligned. To sync audio, the system encodes sound into a compressed representation aligned with visual tokens. During denoising, audio and video latents receive matching guidance, so events co-occur. For example, the model learns that a mouth movement token should align with phoneme energy in audio tokens. The result: tighter lip sync, coherent footsteps, and consistent ambience. But this extra capability increases compute and training cost. Speaking of cost, why is video generation so energy intensive? Let's quantify it. Video multiplies work. 1 second at 24 FPS equals 24 images to generate and denoise across many steps. Add transformers, super resolution, and audio, and each clip becomes heavy. Training these models requires massive GPU farms and long runs. Inference still drains energy at scale. Researchers are pushing hardware acceleration and algorithmic shortcuts, but the footprint matters for sustainability and cost. Next, we'll examine ethical risks that grow with realism and compute, and what tools exist to help. Realistic video raises misuse risks. Hyperreal fakes can spread misinformation. Training on web data encodes biases. Deepfakes violate consent. The industry is building provenance standards and metadata schemes to tag synthetic media. Tools like cryptographic attestations and content labeling help audiences and platforms identify synthetic clips. Transparency doesn't remove misuse, but it creates accountability. Next, I'll cover the evolving legal terrain around copyright and likeness, and what creators should watch for. Copyright and consent are unsettled. In some jurisdictions, purely AI-generated art lacks protection without meaningful human authorship. Using a real person's likeness without consent can be illegal and violates platform rules. Provenance standards like C2PA aim to attach origin data to media so viewers can trace edits. Creators should label synthetic content, avoid impersonation, and check platform policies. Next, who's building these tools and how their strengths differ in practice? Different systems emphasize different strengths. One model prioritizes temporal coherence and physics-like behavior. Another pairs high fidelity with integrated audio. A third offers rapid iteration and creator controls for editing. Your choice depends on budget, desired control, and clip length. Try a few tools for the same prompt to see differences in lighting, motion, and artifact types. Next, I'll list common limits you should expect right now so you can plan around them. Expect familiar limits. Text and logos can wobble. Hands still glitch in complex poses. Water and crowd physics remain hard, and long narrative coherence degrades without careful planning. Fast cuts may introduce flicker, unless the model knows about transitions. None of these stop you from making great clips, but good planning and post-work are essential. So what's next for the field? Let's glance at the near future and emerging capabilities. Watch for joint audio-video models, better scene memory for longer coherent shots, and models that learn common-sense physics to anticipate cause and effect. Expect 3D consistent generation that preserves structure across camera moves and tighter editing tools that combine generation with precision masking and relighting. Efficiency will improve through new architectures and hardware, and on-device models will enable mobile creative workflows. Before we finish, let's run a tight recap of this step-by-step generation process. Recap. Your prompt becomes an embedding. The system chooses duration and initializes latent noise. It may take references or depth cues. A diffusion denoiser iteratively removes noise in latent space while conditioning on text. Transformers attend across space and time to enforce consistency. The latent decodes to pixels. Upscalers and interpolation polish frames. If audio is included, it's encoded and co-denoised or aligned afterwards. Finally, post-processing stabilizes and grades the clip. Now try that shot list prompt and see what happens. If you found this useful, like and subscribe for more clear explainers. Drop a comment with a prompt you want me to analyze in the next video.